Okay, so 7.5 is titled Complex Fractions. I know fractions are everybody's favorite topic, and so to make it more fun, we're going to put fractions in fractions. No, I know it's not everybody's favorite, but I'm going to give you some tips and tricks to hopefully help simplify these to where we're not dealing with super complex fractions for a really long time. We get them as simple as possible. So a complex fraction is a rational expression that has a rational expression in its numerator, denominator, or both. AKA, you've got a fraction, and I wrote out a whole bunch of different examples to where you can see, like the first example just has a fraction on top and a whole number on bottom. Next one, you have a little bit of an expression on bottom with that 4x in the bottom. And then we just get more and more and more complicated as we move from left to right in these examples. All of these are considered complex fractions, though, even if you only have a fraction in one of the positions, the numerator or the denominator. But most of them that you encounter in your homework are fractions on top and fractions on bottom. And so we're going to learn a couple of different ways to kind of approach these problems. I wrote down some steps. There's 3 steps in solving complex fractions. And then I'm also going to make sure and work C 2 different ways so that you can see which way you prefer. Sometimes it's easier one way, sometimes it's easier another, and you get to pick which way to approach these. Like all fractions, you want to always make sure you get it simplified as far out as you can. And like most of our problems that deal with fractions, we don't like playing with fractions for super long, so I'm going to show you how to eliminate some of the fractions or how to simplify them quickly so that we're not dealing with fractions and fractions as the entire problem. So here's the 3 steps that we're going to start with. When you're solving complex fractions, you want to add or subtract the rational expression so that there's one rational expression in each, the numerator and the denominator. AKA, we don't want to have a fraction plus a fraction minus a fraction all over another fraction minus a fraction. Like, you want to condense your fractions. If you can have just a single fraction on top and a single fraction on bottom, your life is so much simpler. Because at that point, all we are doing is dividing fractions. We did this way back, if you ever took Math 20, in 1.3. The very first lesson in Math 20 is all about dividing fractions. I mean, we do everything else as well, but it is addressed there. And so that's really how you're going to approach these problems, is once you have a single fraction in the numerator and a single fraction in the denominator, then step 2 says you multiply the rational expression in the numerator by the reciprocal of the denominator. AKA, you keep it, change it, flip it, just like we would have with any other fraction. We'll write it horizontally instead of vertically. That way we can keep it, change it, flip it. That's what step 2 says. And then 3, you simplify as needed. So the hardest part is really you're kind of combining multiple fraction problems at once. Because when you're doing the numerator, you're going to have to add or subtract those fractions to get a single fraction. That would have been a whole problem all on its own. The same thing with the denominator. If you have more than one fraction in the bottom, you're going to have to combine those. That would have been a whole problem in its own. After that, when you have a single fraction and a single fraction, then you're dividing by fractions, which is a whole other problem. So complex fractions, they are complex because what we're doing is really 3 different fraction problems all together. Or at least that's the most amount of fraction problems you'd be doing all in a single problem. So we're going to approach them this way, and we're going to do A, B, and C using this method. And then after we solve C using this method, I'm going to show you maybe a trick, and either you like it or you won't, and you can use it or you don't have to. All of your complex fraction problems will work with these 3 steps every single time. And I can leave the 3 steps up, I think, for all of A, and then they will have to disappear. So A is going to be AB squared over C to the 3rd power, and all of that is over A over B C squared. And I tried to make the main fraction bar obviously way big so that you can tell where the fraction on top is versus the fraction on bottom. this is considered a complex fraction. We've got a fraction over a fraction, but this one's actually about as simple as they will come because we already have just a single fraction on top, we have a single fraction on bottom, and so we can automatically rewrite this horizontally using a division sign, which I think is easier with visualizing what we're going to do. So when you write it horizontally, the top fraction stays exactly as it is. And it becomes the first fraction you write. That's a 3. And then this big divide bar, this big fraction bar is division, so I'm going to write divide. And then I write my bottom fraction just as it is. These are exactly the same thing. The complex fraction on the left means exactly the same thing as what we've written here on the right. But what we've written here on the right, we know how to play with. Because when you divide a fraction by anything, you keep the first fraction, you change it to multiplication, and then you flip the second fraction. So this will become, the first fraction stays, you keep it, then you change to multiplication, and then we're going to flip our second fraction so that it's bc squared all over a. Now we're going to multiply fractions. And when we multiply fractions, we multiply straight across the top and straight across the bottom. Now at this point you want to simplify. Or if you're looking at my handwritten notes, I simplified before I did multiplication. Remember, either way works. Most of the problems that I work from here on out, I will do the simplifying before I do the multiplying. I just think it's a little bit easier, but you can do it after the fact, and that's what we're going to do here. When you simplify a fraction, you're asking what does the top have in common with the bottom? Do we see anything that the top has in common with the bottom? It's got an A, so those are going to cancel. So got anything else in common? It's got a c squared, yeah. Because on top we're going to have c squared, so that's c times c. On bottom, we could rewrite that as c squared times c. So notice that we have a c squared on top and bottom. So our final answer for this problem would be b to the third all over c. Because once we've canceled everything out, that's all that is left. And you would get that answer by simplifying on the back end or simplifying on the front end. Either way would work. But you keep simplifying until everything in common has been canceled out. Are there questions? Because this one is about as easy as they're going to come. On your homework, heck, I don't think we even start with one that easy on your homework. Nope, we don't. Questions? Okay. Let's do another one. This one's obviously more complicated than the one above. This one has a binomial on top and a binomial on bottom. We don't have a single fraction on top or on bottom because we have 1 plus 1 over d. All of that's over d minus 1 over d. These problems in 7.5, you are not solving. You will be simplifying. The difference between solving and simplifying is simplifying, you will not find out what your variable is. When you solve for something, that is when you actually find out what the numerical value or values are that a variable stands for. And so these are all simplifying problems. We take it out until we can't simplify any longer. So step one of our solving or simplifying complex fractions is we need to have a single fraction on top and a single fraction on bottom. So I'm going to basically pretend like the bottom half does not exist for a minute. And I'm just going to look at the top half and try and figure out how I can write this as a single fraction. So I'm trying to add 1 to 1 over d. Well, I can change 1 into 1 over 1, but that's still not going to help me. I need to have a common denominator. So what would be a common denominator for the top? Do what? Yeah, D would be a common denominator. Because I can change 1 into 1 over 1. And then, like you said, a common denominator would be D, meaning I need to multiply that 1 over 1 by D over D, which will give me D over D. You are correct. So it gives me D over D plus 1 over D, which, to combine that completely, would give me D plus 1 all over D. Sorry, I kind of ran out of room. There we go. So that is the single top fraction now that I have. I have found a common denominator. I have combined using the addition, which is what the problem stated. This is the result. I can kind of do a long one like that. Now I'm going to do the exact same process for the bottom. The bottom, I had D minus 1 over D. That D is like a whole number, so I can stick it over 1. And then I'm looking at D over 1 minus 1 over D. What would be the common denominator for that? Yeah, it'd be a D. Because just like up here, we had a D as our common denominator. Down here, we have a D as our common denominator. Now, that doesn't always happen that way, so don't assume that that's always going to be the same. But in this one, it is the same. So that means I need to multiply this first fraction by D over D so I can have that common denominator. When I do that, I'll end up with D squared over D minus 1 over D, meaning I have D squared minus 1 all over D. This over here is my complex fraction once I have a single fraction on top and a single fraction on bottom. So from that stage, I can do the horizontal writing, where I take the top fraction and I write it first, the D plus 1 all over D. I write my division sign, and then the D squared minus 1 all over D. So we keep the first, we change the operation, and we flip the second. Keep it, change it, flip it. Now, I'm going to choose to simplify before I multiply. Because really, you could just extend the fractional bar if you really wanted to and put the multiplication sign above and below, and that's really all we're doing. So if we're looking at this, do we automatically see anything that the top is going to have in common with the bottom? Yeah, they're going to have that D, because that D would be distributed in here, and that D would be distributed in here, but let's cancel them before we do any of that. All right. Do we notice anything else that looks slightly familiar? Maybe from our Chapter 6 material. We got a D plus 1 on top, and a D squared minus 1 on bottom. Yeah, this right here is our difference of squares. That's one of those special factoring things that I told you you would definitely want to memorize that one. Because we have something squared minus something squared, which means it factors into D plus 1, D minus 1. And once you've factored it, what does the top have in common with the bottom? That D plus 1. So notice everything on top goes away. When you simplify and everything goes away, that doesn't mean you have 0. It means you have 1. Because we were dividing, not subtracting. So be careful about that. I've seen that a few times where everything will kind of eliminate and they're like, oh, it's 0. No, because when we multiply by 1 to keep the same thing. Now, you could have distributed, you could have multiplied first, but the risk you run is that you're not going to see the difference of squares, obviously, if you distribute that D inside. So I find it's a little bit easier to simplify before you do the multiplying, especially if you have stuff with differences of squares or you have these binomials that are going to potentially cancel out. Just because you have a binomial doesn't mean it will always cancel out, but it's always a good rule of thumb to try and look to see if there's anything that's factorable, as we've learned in Chapter 6. Are there any questions or clarifications on this problem before we do C? C is all numbers, but we're going to do it two different ways. Okay. And I'm going to write it a little bit color-coded because I think it'll help us as we work through it. Move it to the top. We have 2/3 plus 1/5. All of that is over 4/5 minus 1/3. Lots of numbers. But like I said, what a complex fraction is we're really doing three different fraction problems all in one problem. We have the addition problem on top, we have the subtraction problem on bottom, and then what we end up doing afterwards is we do a division problem with it. And so that's the way that I approach this. And so in my handwritten notes, and one of the reasons why I color-coded is I pulled the top over to the side for a little bit and I played with it until I got a common fraction. And then I went back up here and just had a shorter space, basically. So all I'm going to think about is the top. I have 2/3 plus 1/5. What is the rule when adding or subtracting fractions? Got to have a common denominator. And luckily for us, the denominators here are 3 and 5, which are both prime. So the way we find our common denominator is we multiply our two denominators together. So the common denominator for this would be 15. So then I ask myself, okay, if I'm trying to get 15 in the denominator, what do I multiply 3 by? 5. But if you multiply the bottom by 5, you got to multiply the top by 5. Remember, that's the whole slicing our pizza into smaller slices. The amount of pizza we have does not change. We're just making smaller slices. And then we do the same thing here for the 1/5. I need to get to 15, so that means I'm going to multiply the bottom and the top by 3. So 5 times 2 is 10/15. 1 times 3 is 3/15. Once you have a common denominator, you add across the top, giving you 13/15. So the 2/3 plus 1/5 is the same thing as 13/15. Now we're going to look at our denominator. We have 4/5 minus 1/3. Same exact process, and actually we have the same exact denominator. It just worked out that way. We're trying to get 15 in the denominator, so I'm going to multiply 4/5 by 3/3. I'm going to multiply 1/3 by 5/5. Give me 12/15 minus 5/15 equals 7/15. Now we've got a single fraction over a single fraction. We're going to write that top fraction first. Divided by the bottom fraction. So we keep the first, change the sign, or change the operator, flip it. So 13/15 stays, we change the multiplication, and we flip it to 15/7. What does the top have in common with the bottom? Those 15s. Those are going to go away. So we're left with 13/7. Improper fractions are totally okay. as long as they are simplified. 7 and 13 are both prime, so that is simplified. So this is the way, using the 3 steps that I told you, and it works every single time. And the next way I'm going to show you how to solve this, it doesn't make it necessarily any easier or any harder. It's just going to be a preference that you will pick working your problems. Before I show you the second way you can solve this problem, are there questions on how I solved it this way? All right, let's look at it a different way. So this will be like C 2.0. Same exact problem. We're going to have 2/3 plus 1/5 all over 4/5 minus 1/3. So obviously we know the answer. We know we're going to get to 13/7. I'm just going to show you a different route to get there. So in the first route that we took, we focused on the numerator kind of by itself. We got a single fraction. Then we focused on the denominator by itself, got a single fraction, and then we did the division. Works every time that way. Another way you can approach these problems is you can look at all of the individual denominators within your smaller fractions. So I have a 3, a 5, a 5, and a 3. For this one, it's pretty simple because we have the same denominators on top as we would on bottom. So that makes our lives a little bit simpler. But that doesn't always work that way, and we'll do problems where it's not always that way. But this one's pretty simple because we have a 3 and a 5 on top and a 5 and a 3 on bottom. So what you can do is you can say, okay, what would be the least common denominator amongst all of my small denominators? What would it be, people? Yeah, it's going to be 15. So if we know the denominator, the least common denominator amongst all of our little fractions is going to be 15, I can multiply the top and the bottom of my big fraction by 15. And I'm going to show you the individual steps in the middle here so you can see what ends up happening. So I'm going to distribute this 15 into each of my fractions on top and to each of my fractions on bottom. So you're going to have 15 over 1 times 2/3 plus 15 over 1 times 1/5. Just distributing. And I went ahead and made it into a fraction so we can do some simplifying. We'll have 15 over 1 times 4/5 minus 15 over 1 times 1/3. This one looks weird because I'd started to write a 5. So notice for this fraction, when I take 15 over 1 times 2/3, that's going to give me 30 over 3. What's 30 over 3? 10. So this first fraction on top goes to 10. Notice the second fraction on top would give me 15 over 5. That goes to 3. So all those fractions on top just went to whole numbers. And on bottom, it'll do the same thing. 15 times 4 is 60. 60 divided by 5 is 12. And then we'd have minus, is it 12? 12, yeah. We'd have 15 over 3 for our second fraction, so that'd be minus 5. 10 plus 3 is 13. 12 take away 5 is 7. We still get 13/7. We still had to play with fractions a little bit. I feel like we don't play with them for quite as long because we didn't have to do individual addition problems across the top, subtraction problems across the bottom. We didn't have to worry about keep it, change it, flip it. All we had to do was distribute that least common denominator into every single fraction that we had. But since it's a least common denominator amongst all of our fractions, then we're going to end up with a whole number in each of those spots, which makes our life a little bit easier. Again, either of these methods works. Sometimes finding that least common denominator is a little bit harder, but it will work if you do the process just like this. So there might be times where you prefer the regular method. There might be times where you prefer this least common denominator method. Just know that either one works. You can even use the methods against each other to make sure you did the work right. So maybe you like method number 1, but you get kind of a weird answer. And so you use the least common denominator method to just double check your work. Because when you have all numbers, yes, you can type all that into your calculator if you're really careful. But most of your problems are not all numbers. Most of them are going to have variables at play, and then you can't type them all in. And so you're going to have to know how to work at least one of these methods in order to be successful on these problems. Questions? Again, you are allowed to pick whichever method you want. I will not require you to use one over the other. All right, let's go on and do D if there's no questions. D, we will have y squared all over 1 over x plus 1 over y. This one's slightly different than all the other ones we've seen. 1, we have more than one variable at play, which we had at the first one. But 2, we have a whole number, theoretically, because we have y squared on top, and then we have our complex fraction part on the bottom. I'm going to do this like the first method, where, because I'm only dealing with one fraction really on the bottom, I'm just going to concentrate on combining the 1 over x plus 1 over y into a single fraction. What would be the common denominator for 1 over x and 1 over y? XY, exactly. This one's got an x, that one's got a y. I need them to have both of these things. So that would mean I'm going to multiply the 1 over x by y over y to get me that common denominator. And I have to multiply the 1 over y by x over x. The y squared is just kind of hanging out up there for a little bit. So you multiply by the y, you get y over xy. You multiply by the x, you get x over xy. Now I can do that addition in the denominator. So I have y squared over x plus y over xy. If you write it y plus x, it doesn't change anything. That's the commutative property of addition. We can interchange the order. It doesn't matter. I usually write them in alphabetical order because I guess I have some OCD on that. Now we have a single number on top divided by a fraction. I can write it horizontally and approach it just like I would any other. Because in order to turn a whole number into a fraction, you stick it over 1. So y squared is the same thing as y squared over 1. Divided by the x plus y over xy. Keep it, change it, flip it. So I keep the y squared over 1. Change to multiplication. Flip the second fraction so that I have xy over x plus y. Now, at this point, if you are like me, I'm looking for things that I can cancel from the top and the bottom. But here's where I like this problem the most, is because you might look at this and say, well, I know I'm going to have a y that's going to cancel. But that's not true. And that's because we have a binomial on bottom. We have two different terms. We have an x and a y. We can't pull a y out of both of those terms. So don't be tempted to do magic math and say, well, I know these y's are going to cancel. I've seen that all the way through. My trigonometry students like to do stuff like that. That's just magic math, so don't do that. We can only cancel things if everything on top has it in common with everything on bottom. And in this case, there's nothing in common between my two terms on bottom that I can pull out. So unless I have an x plus y on top, there's nothing that I can cancel. So I'm going to end up with an xy to the third all over an x plus y. I can't cancel the x because my y term on bottom doesn't have an x. I can't cancel my y's because my x term doesn't have a y. This is as simplified as it's going to get. So you do want to be careful that you don't try to oversimplify things by doing magic math. Questions? All right, let's do one more. Let's do 12p to the third all over 7r squared s all over 9p to the fourth all over 14r to the third s squared. So this is going back a little bit to like the first problem we did. And while you don't have homework problems necessarily like this one, I like problems like this because it causes you to look for things the top has in common with the bottom, and it really does help you hone in on how to simplify. So since we already have a single fraction on top and a single fraction on bottom, I'm going to write it horizontally and then keep it, change it, flip it. And if you're comfortable with skipping the step where you write it as the horizontal first and you just go straight to keep it, change it, flip it, you're allowed to do whatever you want to do with that. I will usually always show more work in my lecture and in my notes, just so that when you go back to reference it, you know what I did, hopefully. So I wrote it horizontally. Now I'm going to keep the first. Change it to multiplication, and flip the second. Now I'm going to start canceling stuff. And I'm going to start with the numbers. You got to start somewhere. I'm going to start with the numbers. I know I have a 7 in the denominator. And I know 14 can be split up into 7 times 2, which means I would have a 7 on top and a 7 on bottom. So those can go away. Now 9 and 12, 9 doesn't go into 12. But I know that 9, sorry, I moved my paper. I know that 9 is the same thing as 3 times 3. And I know I can write 12 as 3 times 4. So that means I would have a 3 on top and a 3 on bottom. Now, don't be tempted to say, oh, well, I have a 4 and a 2. I can cancel those. No, you can't because they're on the same side. They're on the top. Those are going to stay. So we just handled all of our numbers. Now we move to our variables. I have a p to the third on top. I have a p to the fourth on bottom. Well, p to the fourth is the same thing as p to the third times p, which means I'd have a p to the third and a p to the third. So next, I look at r, and I do the same thing. I have an r to the third on top and an r squared on bottom. So that's r squared times r. So the r squareds are going to cancel. And then I have an s on bottom and an s squared on top. S squared is the same thing as s times s, which means you have one s that's going to cancel out. Now, obviously, that's kind of a mess looking at it. So you definitely can take more than one step doing this, or you could multiply it all through first and then divide. The only risk that you run is if you multiply it all the way through at first. Yeah, the variables are a little bit easy to spot because you're basically asking where do you have more of them. But you would end up numerically, I don't know what you'd end up with numerically. You'd have 12 times 14. That's quite a large number. Let's see. Which is 168. over 63. If you multiplied your numbers, like if you did all your multiplying first, that would just be the number portion. And I don't know about you, but looking at that, I wouldn't know straight off the top of my head if that's simplified or not, because I have an even number on top and an odd number on bottom. So you have to be really diligent, is what I'm saying, if you choose not to simplify first. Because you will have to go through all the factors and say, okay, does 2 come out of both of these? Does 3 come out of both of these? Does 5 come out of both of these, or 7? Like, you'd have to ask these questions in order to actually get your simplified answer. If you do the simplifying first, then while this looks like a mess, I'm just looking through trying to find the things I haven't marked out. I have a 4 times a 2. That will give me an 8 RS. That's my top. There's nothing left here on the bottom, on the left one, and then I have a 3 and a P. So while this looks messy, if you stay good about how you're marking them, or even if you use a highlighter, or if you used another color to really like showcase what's left, it's not actually bad. It just looked a little messy. If you do all the multiplying straight through and then decide to simplify later, make sure you're really good about finding those common factors between numbers, especially. With your variables, it's going to be a little bit easier. With your numbers, though, you could get stumped and say it's 168, and then you cancel out all your variables, and you have RS over P, and you're going to get it wrong. So be careful about those. Are there any questions about how I did that problem?